All right, Calvin Ho, homework 17. Given this first problem, we have initial um, angular velocity of 300 RPMs per second. We know there's a requirement of 1,800 foot-pounds of work that must be done. We're on a flywheel, and we know that the desired end speed should not be less than 90% of the original speed. So, A, determine the required moment of inertia of the flywheel. So we have our initial, and we just convert it over to radians per second. And we have our final, and we know that's how much work is done. So we use our equation right here. This T1 plus the work equals T2. We know T1 equals this 0.5 I for inertia, and then the initial angular velocity squared, T2 equals 0.5 inertia, the final angular velocity squared. And then we're just going to plug into this equation and solve for the moment of inertia, and we find that it's 19.2 pound-feet per second squared. Okay. So pretty easy. B, we have this constant 25 pounds-foot couple in the shaft of the flywheel, and we want to know the number of revolutions for that constant. So we have this, the work equals this constant times the revolutions. We know the R constant, this should be capital M, mass. So we use the constant it gives, solves for the revolutions, and we get 11.5 revs. This is what's required. So question 2, we're given the slender rod, just of general L and W to start, is released from rest. That's the important part. So we know that like velocity, angular acceleration, angular velocity, and things like that at this point is 0. And we know it swings freely, and we're asked to determine the angular velocity as it passes through this vertical position, as well as the corresponding reaction here at the pivot. So yeah, so once it hits this point, it's completely horizontal, so all the acceleration is going into the upward into the coupling. So we start here. We know our velocity at this point is RW squared. R is just half of the length. W squared is where our velocity is. We know T2 is this equation here, which would be our right here. So for T2, we get this 1/6 mass times length squared, this angular velocity here squared. We use our T1 equals T1 plus work equals T2. We know this T1 is 0 because it's released from rest. And then by solving that, we get we get our angular velocity at the second position equals the square root of 3g divided by the length. Sorry, I just want to work this. And we also know the work is equal to mass times gravity times r, so that L1/2. And then we plug that in, and we were able to find this second angular velocity. Anyway, so we know that the normal acceleration is just the radius, which is that L1/2 times our angular velocity squared at the second point, where we'll solve that the acceleration is 3 times the gravity, our gravity, 3 times our gravity divided by 2. We're able to sum all the forces here, let it equal to our kinetic diagram, and we get this reaction at A minus our weight equals mass times acceleration, because since there is nothing here, we know this V2 is equal to 0. And then we're able to solve for our reaction to be this 2.5 mass times gravity upward. For part B, we're asked to solve if our weight is 1.8 pounds and our length is 3 feet. So we plug in those values into our equations we found here. We get the angular velocity at the second point is 5.67 radians per second, and our reaction at A is 4.5 pounds upward. Alright, moving on to problem 3. We're given this frame here from A, B to C. We know they're welded together in an L shape. Right here at this position is pushed in, but is from rest, is let go, and then we know it locks out at 90 degrees. And we want to find the angular velocity for when the assembly passes this 30-degree position. Yeah, so we just drew our two other positions here at 30 and at 90. We calculate our inertia at B here, 1/3 m of AB, L to the power 2, same thing here, but for BC. We know the masses have to be the same since they're identical bars with the identical lengths. So we're able to simplify it and just get AB to equal 2/3 m L. This should be capital L squared. Okay. We're calculating the velocity at 30 degrees. Get weight h of AB, then weight times h of BC. Able to simplify it here into just the angles, into the weight times L divided by 2 sine 30 minus L divided by 2 cosine, and this should be of 30. And then we're able to calculate this t here to be 0.5 I inertia at B, angular velocity to this angular velocity here squared. At 90 is a little bit simpler. No, velocity is just the weight times the length divided by 2, and this t for kinetic has to equal 0 because at this point it stops, so it's no longer moving. I'm using the conservation of energy. We know this kinetic plus this velocity at 2 has to equal the kinetic plus the velocity at 3. So we plug that in here and we're able to solve for this angular velocity at the second position, and it equals 7.09 rads per second. So not too bad. Part 4, we're given this wheel here, this lug that's 50 millimeters from the center of the automobile wheel, and it's applying this force for 0.10 seconds. And then we're assuming the wheel starts from rest. We're asked to find the resulting angular velocity of the wheel, given that the mass here is 19 kilograms and the radius of gyration is 250 millimeters. So since it's starting from rest, we can just calculate that this mt equals this inertia times the angular velocity. So we're able to find our inertia here for mass times the center radius of gyration squared. Able to get 1.188 kilograms times meter squared. Able to calculate the applied couple, M equals the 100 newtons times 0.46 meters. This equals 46 newton times meters. Take the sum of the moments here. We know this applied couple times T has to equal the inertia times the angular velocity. Solve for the angular velocity. We get 3.87 radians per second. Okay, going on to problem 5. We're given the sphere here, radius r, and mass m. It's going through a rough surface, so we know there's a friction on it. And we know that the initial velocity is our sum, so initial angular, initial velocity. And then we know the final velocity needs to be 0. We're asked to find A, the required magnitude of the initial angular velocity, as well as the time required to go to come to rest. Yeah. So we start by drawing our moment of inertia and impulse diagrams. So our moment impulse diagrams. This is what we get here. The inertia times the initial angular velocity, the mass times the initial velocity. We got our weight times time, normal force times time, friction force times time, and we know it goes to rest, so this is all 0 over here. Summing the forces in the y direction, we get that the normal equals the weight, which equals mass times gravity. Summing forces in the x, we get this here, and we get this friction force times time equals the mass times the initial velocity. If we sum the moments around the center, we find this equation here, and we're able to solve it for the initial angular velocity in terms of v naught and r like it requests, and we get 5 times v naught divided 2 times r. Yeah. Then we also know that friction force has to equal to the friction coefficient times the normal force. We know the time for it to come to rest, this mass times this initial velocity has to equal this friction force, but we plug in what we found here, how the normal force equals the weight, so we find that the friction coefficient times mass times gravity times time. We solve for that time, and we find that the time required for the sphere to come to rest equals mass times the initial velocity divided by the friction coefficient times mass times gravity. Yeah, so not too bad there. Okay. For part 6, we're given this semi-panel R that's connected to this full circular plate. And then we know that they're the same thickness and the same material. And we know that the whole assembly is rotating with this initial angular velocity. And we're asked to determine the angular velocity of the assembly after the panel has been released and comes to rest against the plate. Yeah. So we know if the mass of the plate is just m, then the mass of this panel is just half of that, because it's just half a circle at 0.5 m. So when the panel is vertical, so this initial start, we know that inertia is equal to 0.5 mr squared plus 1 over 8 m times r squared. And then this angular momentum here is this inertia times the initial angular velocity. We do the same thing for when the panel is horizontal. So at the second position, the second moment inertia is this 0.5 mr squared plus 1 over 4 m times r to the power of 2. And then this second angular momentum equals this inertia, second inertia, times the second angular velocity, so when it's completely down. Yeah, so this final position. Knowing that these have to be equal for the conservation of angular momentum, we're able to plug in what we found here and solve for our second angular velocity, and we know that the second angular velocity we're going to find equals 5/6 the initial. Yeah. All right, for question 7, we're given this bullet is hitting this wooden disc, and then we're asked to determine the linear velocity and the angular velocity immediately after the bullet has penetrated the disc. So we start with our momentum impulse diagram. This part, the disc is at rest, and we have the velocity of the bullet. This here. We go in sum the forces in the y, and we get that the normal force equals mass times gravity. We sum the forces in the x direction. And since it's immediately after the bullet, we know t equals 0. So we get v equals this mass times the initial velocity divided by m. Yeah, so that's the v right there. We're going to sum the moments around the center. Do the same thing where we know t equals 0 at that beginning time, and we're able to solve for the angular velocity, which is this m, the initial velocity divided m, this moment times r. For part B, we're asked to describe the ensuing motion of the disk and determine its linear velocity after the motion has become uniform. So we're going to sum the moments about this point A that we have here. And then with v equals the radius times the angular velocity, we're going to plug in the values that we know. And then we find that this, I'll call it v2, and this angular velocity 2 equals these equations here. Because we're going to solve this equation for this W2, and with that W2, we're going to plug it into our V2 equation up here. Let me just fix that. Comparing this to the equations we found before, we can conclude that the disk is going to slide to the right while spinning counterclockwise, and eventually it'll just start rolling afterwards with this at this velocity that we find. Okay, on to part 8, question 8, we're given these two people. One's jumping off of this height, HA. It's jumping out of this plank and launching up this person at A. So we're given the mass of the plank, the mass of this person here, and the mass of the other person, and this height. And we're asked to determine the height that gymnast A will rise. Okay, so we're going to start with our impulse momentum diagram. So the person hits here, here, and then the forces down and up. Okay. And then they have to be equal, so we're going to sum the moments about point D here. And get this equation here. And knowing that V2 equals this length, L, times the angular velocity, we can solve this equation for the angular velocity 2 and get this equation here. We know V1 is equals square root 2gh, which equals 7 meters per second. V2 equals this length L times this angular velocity 2 that we found up here. We plug in our values. that we know and solve for V2 equals 3.77 meters per second. Well, we know that V2 also equals square root 2 times G times this H that we're finding. We're plugging in the values and this V2 that we found earlier, and we're able to find the height that this person at A goes is 0.724 meters up.